Okay, so I guess we're right on time and we can start. So welcome everybody. Our speaker today is Cyril Letrouit, and it was so nice to actually write the title at the blackboard, and that's quantum mixing on large Schreier graphs.
Thanks a lot for the invitation, Camillo, and thanks for being here. I am very glad to speak here. So it's a joint work with Charles Bordenave, who is here, and Mostafa Sabri. It's about spectral theory of graphs, and I will first start with a light introduction about the subject. So we are dealing with graphs. So for me, a graph is just a set of vertices. V is the set of vertices that can be finite or infinite, and then connected by edges which are non-oriented. And all my graphs, even if they are infinite, they have a bounded degree. And so the adjacency operator is simply AF of x. So AF of x is equal to the sum over all y's that are connected to x of f of y. And so since I assume they have bounded degree, it's self-adjoint, and we can consider the spectral theory of these kind of things. And this is what we will do, and especially we will be interested in finite graphs converging to an infinite graph. And so we have there is a natural notion of convergence for graphs, and it's the notion of Benjamini-Schramm convergence. So Benjamini-Schramm is the following. You have a sequence of graphs that has n. Each of them has there's n vertices in Gn, and we say that it's converging to a graph that is infinite and that is rooted. So there is a pointed specific root in the graph G, and so we say that Gn converges to Ge if in words, it's just that if you take a typical point in you fix a number like 10, you take a typical point in your Gn, and you look at the ball of radius 10, and you want that for a typical point, this ball of radius 10 is isomorphic to the ball of radius 10 centered at E in the graph G. Okay, so you want that for any R. 1 over n times the sum from 1 to n of the characteristic function of the ball of radius r in Gn and centered at ball of radius r centered at x is isomorphic to the ball of center E and same radius, and you want that this goes to 1 as n goes to infinity. So that's a very classic notion, and the thing is that it's a very good notion also for spectral convergence. So in the sense that if we consider the spectral measure of Gn, so it's simply, let's call it mu n, which is 1 over n sum of delta lambda I, where the lambda i's are the eigenvalues of the adjacency matrix of Gn. Okay, then it converges weakly to the spectral measure of G under this assumption. So first, what is the spectral measure of G? So of course, my introduction is it's basic material, but spectral measure of G, and so what is the spectral measure of G? Is just so it's first if we take a point in G that is x, so delta x for any h that is continuous, you want that your and the adjacency operator is A, okay? you want that delta x h of a delta x. So this is typically you imagine h is a polynomial. It's equal to integral of h of lambda d mu x of lambda. So that's the definition of the spectral measure, mu x. And if you assume that your limit is homogeneous, so what we will consider is the limiting graphs. They are transitive. They are Cayley graphs, and so actually this mu x does not depend on mu or on x. In our setting, and so we call it just mu. And so the proposition is that Benjamini Schramm convergence implies mu n which weakly converges to mu. That's very easy to prove. So then the question is, if you know some information on mu, what can you infer so first for the eigenvalues, it's kind of, this gives you some insights on the distribution of eigenvalues for Gn, but you can be interested also in the eigenvectors. And the thing is that how the measure mu decomposes in terms of pure point, absolutely continuous spectrum, and singular spectrum is very important to understand, for example, the eigenvectors of Gn, and that's the topic of the talk. So what you do is you decompose mu in terms of its pure point part, its singular continuous part, and its absolutely continuous part. And the thing is, so again, it's something very important in mathematical physics. So the pure point part accounts.
Assuming G is homogeneous.
Yeah, I'm assuming G.
So it's basically a Cayley graph.
It's a Cayley graph.
And so yeah, I guess I know a few examples. There aren't many examples where you can compute these things.
No, exactly. So yeah, it's important to say. So
I mean, we're not a tree right now. That's too.
Yeah. So there is the tree, regular tree. There is the ZD that you can compute. There is absolutely continuous spectrum. Then there are also some other examples. For example, Lamplighter groups, where there is some absolute. There can be, depending on the generators, there can be some singular continuous or dense pure points. There are some.
Another one. You know McLaughlin's thesis, John McLaughlin?
No, I've never read it. No.
A student of mine from another century. He computed you can have you can have some point spectrum in the continuous.
Yeah. I mean, these three things do not need to be. I mean, their support can intersect. But so the pure point spectrum is responsible. Usually, it has so it corresponds to the eigenvalues usually, and the states. So the effect on the dynamics is I mean, if you have a state, its energy, depending on where it lies, to which part of the measure it belongs, will have a big influence on the dynamics. Meaning, if you consider the Schrödinger operator e to the minus eta psi, and you look at large time, when time goes to infinity, so there is a whole bunch of theorem which is usually called Rage theorem that tells you that if psi is in the part, okay, it's an eigen, okay, its energy is in mu pp, for example, will tell you that e to the minus eta psi remains localized. Okay, you remain at the same place roughly in the graph. Then, if you look at the absolutely continuous spectrum, it corresponds to states that whose energy will go to flow in the graph out of the very far, and so it corresponds to conductivity. Usually, this is what we say. It corresponds if you model electrons, etc. The absolutely continuous spectrum would model the conductivity, the energy that is able to move, that is mobile. And usually, finally, the pure point spectrum is better understood. So if you think, for example, of Anderson localization or thing like this, pure point spectrum is better understood. And so here we focus on just the absolutely continuous part. The singular continuous part is something very subtle. But here we focus on
an example of a group with some generators for which it's singularly continuous.
Yeah. Lamplighter groups.
Oh, lamplighter.
Yeah, depending on the generators, but you can. And even I think there are some also nilpotent groups where you have related to the Hofstadter butterflies. Okay. So we focus on the absolutely continuous spectrum. And the question is, so we assume that we have absolutely continuous spectrum in the limit. We assume Benjamini Schramm convergence of a sequence of graphs. And the question is, what can you say? I said already, what can you say about the eigenvectors of the GN? Okay, if you know that in the limit you have absolutely continuous spectrum, and you know that your graphs, somehow your finite graphs, they look like the infinite graphs. What can you say about the eigenvectors? And the answer is you expect them to be delocalized. So this is what I said here. Pure point correspond to localized states and absolutely continuous spectrum to delocalized states. And here what it means, there are different definitions. There is a first one. So delocalized roughly would mean that you expect that on Gn, if you take psi in some part of the spectrum where there is in I where there is AC spectrum, you take psi. I will make it, but you expect that psi has energy roughly the same at each site of the n sites. Okay. That's so psi, you expect that somehow psi at x is roughly of order 1 over root n if you have normalized your vectors L2 of v is equal to 1. Okay. For any x, you expect this. And typically, so there is one first definition of delocalization would be that it's the definition with L infinity norms. So one definition of delocalization would be that you are able to say that psi n, so psi in the graph, is lower than 1 over root n. So this is very optimistic. Maybe there is some loss here, okay. Maybe a logarithmic loss or something. This is a very strong result because then you know that your eigenvector is really well spread on the graph. And there are only few examples where we know that it's true. For example, random settings, random regular graphs, or some models of random matrices. But this is not what we will do today. So today we study quantum ergodicity. So it's a different notion that is not implied by L infinity norms, but and it's unrelated. I mean, there is no implication between the two, but usually, this kind of very strong results could be thought as stronger than quantum ergodicity. So quantum ergodicity, it's the idea that if you want that your eigenvector is well spread on the graph, what you do is to test against observables on the graph. So if you have your graph, for example, you have n very large, and you take a, which is the characteristic function of half of the graph, for example. You take a, which is 1 lambda, where lambda is half of the vertices. And what you would like to do, to say, is that sum of psi n of x squared, you've picked an eigenvector corresponding to Gn, x in lambda, you would like to say it's roughly 1/2. Okay, or the size of lambda divided by n. you would like to say this, and more generally, you would like to say that the definition of quantum ergodicity is you pick a sequence of observables. So these are observables. This means AN from B to C. And always we assume that AN, N infinity norm on the graph is lower than 1. So it's Vn. And you want to say that for any orthonormal basis of Gn, you want to say that the sum of psi alpha, so the nth eigenvector, so you have for any orthonormal basis that I denote by psi n alpha, so alpha in n, and the corresponding eigenvalues are the lambda alpha. You want to say that psi alpha n, an, psi alpha n, so this is your test. You subtract the mean of an, you take the square. So, and then you sum over lambda. So you sum over all alphas, for example, alpha in n. And you divide by n, so you take the mean. You want it to go to 0, as n goes to infinity. That's the definition of quantum ergodicity. And if it's true that for any sequence of observables and for any orthonormal basis, you have this going to 0, you say that quantum ergodicity holds. And typically, you should imagine that an is, for example, a characteristic function of some fraction of the vertices.
The orthonormal basis is somehow related to, is composed of eigenfunctions?
Yes, because you are in the finite graph. It's the orthonormal basis of eigenfunctions, sorry. Yeah. Yeah, it's only orthonormal basis of eigenfunctions. Of course, sorry.
For any orthonormal.
Not for any orthonormal basis. This would be false. Yes, sorry about that. Okay. So it's inspired by the same notion on manifolds, but on manifolds you don't. I mean, it's a bit stronger because here you have a growing family of geometries, so it's different than having a fixed manifold. But there is this theorem by Schreier, Colin-Dardier, and Zeldich that says that on a manifold, on a compact Riemann manifold, if you have a ergodic geodesic flow, then the quantum ergodicity holds, and this quantum ergodicity, in this case, tells you that this, up to a density 1 subsequence of eigenfunctions, converges to the Liouville measure, the integral of an over the manifold. Okay, so what we do is to prove that this holds. So again, this really means that somehow the psi alpha n are, so I didn't explicitly explain, it's the scalar product in N2 of V, okay? And this is the mean of an. This is true. So what we will do is so this has been proved for periodic graphs. So think of, it's very easy, it's z over z over to the d. For example, this is Gn, and this goes to Cd. Then we know it's true. And it's also true for regular graphs, and more generally, when the limit is a tree. Then people know how to prove this. So this result is.
Then you have to put some.
You have to
put some other conditions.
Yeah. So periodic graphs, it's a result due to Mackenzie and Sabri, and for when the limit is a tree, actually you need to put some assumptions. First, that the sequence of graphs Gn is an expander, and secondly, that you have some control of the resolvent of the limiting tree. So it's In this case, you use block flow-K theory because everything is periodic, so you can use kind of standard tools. And here, in this case, you use recursive equations on the resolvent because the tree, you know very well the path, so you know the resolvent has some kind of product structure. And so this is a very specific case, the periodic graph, but here it's very important that you have no cycles in the limit. You can have some cycles in the finite graph, but in the limit, you shouldn't have any. And
that the Benjamini Schramm convergence to the tree. Or...
Yes,
sure.
Yeah, exactly. Yeah, the Benjamini Schramm convergence to the tree ensures that you have few cycles. At a typical point, you would have few cycles that close to this point. Okay, so the result, so now the setup, the real setup. So I need just so that everybody is on the same page. So the setup is the following. We take gamma, which is a finitely generated graph group, and so a Cayley graph. So it's just you take a set of generators of gamma, and you consider so the Cayley of gamma and S is just so in this case you have V, which is the set of vertices is just gamma, and you put an edge, so an edge where between X and Gx for any G in S. Okay, that's a Cayley graph. And what we are doing is, so a Cayley graph is something rather rigid and specific. And that's our infinite graph is a Cayley graph. Okay, infinite is Cayley. But it's much more general than just the tree, of course, which corresponds to the free group. And the finite graphs that approximate the Cayley graph are Schreier graphs. And that's a very common way to approximate a Cayley graph, and I will explain how. So finite graphs are Schreier. So the definition is the following. You take rho n, which is a permutation valued representation. So it's a morphism from gamma to Sn, the group, the symmetric group of permutations. Okay. And we consider the Schreier graph gamma S rho n. It's what? It's exactly the same. You do you roughly do the same. You put so the set of vertices is 1 to n. Okay, and the set of edges you put an edge. Okay, I forgot to say my set of generators here has to be symmetric so that I have a simple thing. Put an edge between x and rho n g of x. Okay, so I permute for any x and g in S. That's my Schreier graph. And so concretely, in the Cayley graph, you have a cycle as soon as you have a relation in your group. And in the Schreier graph, you have the same relations due to the fact that you have a morphism and you have exactly the same relations, but you can have more actually cycles in the Schreier graph than in the Cayley graph. Just because your rho n g of x can be equal to x actually sometimes. At least when g is equal to e, it's always the case, but sometimes for other g's, you can have rho n of g of x, which is equal to x, and then this would mean that you have a cycle. Okay? So now the adjacency operator is, of course, just in the Cayley graph, it's just sum of so the adjacency operator in Cayley graph. It's sum of lambda of G for G in S, where lambda is the left regular representation. So lambda of G delta X is delta of GX. That's the adjacency operator. And in the Schreier graph, it has exactly the same form, except with rho n. And actually, we will look not only to these operators, but also to weighted versions. It's with this, it is no cost to look also at weighted versions of this. So we also look at sum of PG lambda of G on Cayley, where PG is just okay, and the same sum of PG rho n of G on the Schreier graph. Okay. And the thing is, you can wonder, when do you have a convergence of these graphs to this Cayley graph? You have the same group, but there is a condition on this representation to say that you have the Benjamini Schramm convergence. Just because there is a proposition that is very easy that says proposition Benjamini Schramm convergence of the Schreier graph gamma S rho n to the Cayley graph. So it's equivalent to the fact that you don't have too many more cycles in the Schreier graph. And this corresponds, the cycles come from the G's for which rho n of G of X is equal to X. And this is related to the trace of rho n of G, of course, because, okay? And so it's equivalent to the fact that for any G different from E, which is the origin of the group, I didn't say, you have 1 over n trace of rho n of G tends to 0 as n goes to infinity. And this condition is called the weak convergence of representation. We can call it this, because it's opposed to strong convergence, which I hope to come to at some point.
Okay. This would be Mackay if you're going to a tree.
Sorry.
In the case of convergence to a tree, I guess it's been in Schramm, but it goes back to Mackay.
Okay.
Mackay, you have regular graphs,
Yeah.
and he counts exactly how many cycles.
Yes.
Okay, that's little.
Yeah, exactly. There is this paper. He counts everything.
It's exactly.
Okay. And so the first result is the following. So if you have, so we want a result again of quantum ergodicity for these Schreier graphs converging to the Cayley graph. And so we assume weak convergence of rho n to weak convergence of rho n. Okay, actually it's to lambda, but weak convergence of rho n. We assume that gamma has that sum of PG lambda of G. Okay, we take, let PG in C to the gamma such that, so C to the gamma is just the fact that it's also, it has finite support. Okay, you have only finitely many PGs which are non-zero, such that the sum of PG rho n of G, lambda of G has absolutely continuous spectrum. So you don't need to have absolutely continuous spectrum on the whole, only absolutely continuous spectrum. You just assume it in some interval. So I0, let's say, and you assume that you don't want precisely to have pure point that appears in the middle of your AC spectrum. You really want to have pure AC spectrum at this place. So the density, so spectral density of the measure, bounded above and below on I0. And then you have some assumption on the sequence of observables, meaning we establish, so this is a very general framework. Compared to the previous results, the difference is that we assume that we have the weak convergence, but to a Cayley graph that may have many cycles, etc., we don't need to have a tree structure, meaning we will not use the recursive equations of the resolvent. And the fact that you're able to allow some loops, the problem with loops in all this stuff is that, for example, when you send an eigenstate, it can come back and it creates many problems in general, or on manifolds on graphs. The fact that you have loops is very bad in general. And this framework, so we are able to deal with loops and to just assume Benjamini Schramm convergence of the graphs, AC spectrum in the limit, and then we prove quantum ergodicity. But the restriction is that we need to assume something on the observables. So AN are asymptotically uncorrelated. And I will explain what it means. But it's a condition, I will say, that is verified for random observables. It's verified with probability 1 if you draw your observables at random. So it's a condition I need to explain. But first, I will.
In Parelman's work, the expansion is used to allow you to take any AN. You're now taking special AN and you're dropping the expansion.
Exactly, but then we have a second result where we put more assumptions and we have again all the ANs, but without the tree assumption in the limits.
But some expansion.
Some expansion, even strong convergence. So the conclusion of the theorem, before I explain the asymptotically uncorrelated thing, is the following. So we have quantum ergodicity, as I said, but here it was written for all alphas, whereas here, of course, since we assume something only in I.
Since you philosophically talking about this, and I think you know Colin de Verdier, right?
He was my advisor.
Okay. So I think you should know. What does it mean for a graph to be ergodic?
Yeah, that's a very good question. But
what does it mean for the motion on a graph to be?
But actually, what we assume, I was just going to say, what we prove is both a quantum ergodicity and quantum mixing. And quantum mixing is something where you also control not only the psi alpha, but also psi alpha, psi beta.
Yeah, right.
And Zeldich had a theorem on manifolds that says that if you have this control also of correlations, then it implies that your flow on the manifold is ergodic. And so here, somehow, we assume, we prove quantum mixing. And so so there is no good answer to your question, but somehow quantum mixing, although, quantum ergodicity is something that is true also, for example, on the torus in the physical space. Quantum mixing is false in the torus. It really implies ergodicity. And so here, our condition, our proof quantum mixing, we prove quantum mixing, it's false on ZD, for example, whereas quantum ergodicity is true. So in the end, to answer your question, quantum mixing, it's really something that needs some growth of the graph. So you need some expansion in the limiting graph, at least. And so that's not a real answer because it's not a dynamical condition, but at least it's something that really sees the ergodicity of the flow. So the conclusion is that if you sum over the lambda alphas that are in I, you divide by the number of eigenvalues in I. You look again at these psi alpha n, an, psi alpha n. You subtract the mean. You put the square. So that if you are able to prove that it's small, it means that for most eigenfunctions, this is close to this. Okay, so most eigenfunctions are delocalized. So we prove that this is true, and we also prove so quantum mixing, which in our context is the following thing: is the fact that here, so here it's I0, here it's a macroscopic interval. Okay, but actually there is also some microscopic thing that is true, and for which you are able to control also the correlations between nearby eigenvectors. And so the quantum mixing thing is the following. So I denote by lambda e eta, which is just e minus eta, e plus eta, for e and eta are real numbers. So we prove the following. We prove that if we consider for any E1, E2 in I0, the mean over the eigenvalues that lie in this first interval, and you also accept correlations with eigenvalues in another interval, but that can be the same. You can take E1 is equal to E2. Then you control also the psi alpha n, an, psi beta n, minus, so it's an, and 1 alpha is equal to beta. Okay. Squared tends to 0. And what it means is that for different eigenvalues, you have this tends to 0. For different eigenvalues, you expect that there is no correlations between nearby eigenfunctions. And this is typically something which is not true on ZD. If you think of ZD, you have oscillations of eigenfunctions, and if you think of exponentials or cosines, you can have nearby eigenfunctions corresponding to nearby eigenvalues, I mean, that have some small shift in the phase that make them actually correlated between each other. And this fails in the ZD case.
Sorry, can you repeat what asymptotically the ANs are?
Oh, okay, so AN, the asymptotically, I didn't say, so asymptotic uncorrelation, it means the following. It means that for any G in your group, you define the correlation of AN with itself at distant G. So you look at AN of X, AN of GX. And when I mean GX, I mean rho n of G of X, okay? You look at the sum over X, okay? And you can subtract the mean, for example. You subtract the mean.
Assume it.
Sorry?
As subject, you should always assume the mean is.
Exactly. Thank you. AN is 0. You're right here. So AN of GX. So you sum over N, 1 over N, and you call this quantity sigma N of G. It's just the correlation of AN with itself at distant G. And so the property of asymptotic uncorrelation is just that the limit when, you want that the lim sup of sigma N of G, you call it sigma of G, okay? And then what you want is, so this is limit of sigma of G when G goes to infinity is 0. It's just the fact that
Right. So in like the geodesic flow case, where you say negative, the hyperbolic surface, the quantum variance, which is what you write down, is asymptotically trying to be the classical variance, which is this quantity, which is the geodesic flow, which is the integral, but then the integral from minus infinity of a classical variance. That's sort of what's manifold case. The feature of that.
And okay, thank you. And the thing is that this condition, if you take, for example, an to be, and you also want, sorry, I didn't say, but it's throughout my talk, you want the n infinity norm to be it's that one. So if you take an, which is a Bernoulli plus or minus one at each side of on your graphs, then it's satisfied with probability one. Okay. So I need to change that. Okay. So few remarks. First, this is a statement for what we call diagonal observables, meaning we just multiply by an of x, but we could also consider, we do it when there is off diagonal things, meaning you can replace by an operator that is supported at finite distance, and it also works. Then, the thing is, you can wonder if this condition is really necessary. And the answer is yes, because if you just assume the first two things, there are counterexamples to this. And there are counterexamples that are not difficult to build, where you take regular graphs, you combine them, and you are able to prove that this is really a necessary. I mean, it's one possible additional condition that is sufficient to prove this. Maybe there could be others, but
well, what's the example? What's the gamma?
The example in the example is gamma is a free group. Free group is just a regular graph that has some specific properties. It's kind of non-expanding also. Okay. And well, that's it, I think. And so the second main result is, okay, this condition we would like, because usually quantum ergodicity you want to for all observables. And so if you want to prove it for all observables, then you need more conditions. And so before stating it, the main condition that we will add is that instead of weak convergence, we have some very strong control of the norm, operator norm of the growing graphs. It's usually you assume it's, I mean, Anantaraman and other people, they assume that you have an expander sequence. And here you will assume even strong convergence of the sequence of representations, which is kind of an analog of or a generalization of Ramanujan graphs. So definition of the strong convergence. So it's the following. It's for any p such that pg minus 1 is equal to pg bar. So for any p, you have that rho n of p. So what I call, did I define it? Rho n of p is just a thing. Okay, so it's your adjacency matrix. Okay, rho n of p restricted to on the constants, it always makes the sum of pg. So it's not very interesting what happens. So you restrict to the, it's exactly the same as what you do for Ramanujan graphs. What is interesting is the second eigenvalue, not the first one. And you want that this converges to the operator norm of lambda of p. And in the tree, okay, in the free group case, in the infinite irregular tree case, it's just here you would have, for example, when p is just a characteristic function of the free generators. It would be 2 root d minus 1, and here it would be, this condition would mean that you have optimal spectral gap in the limit. Okay, but here you assume this for any p. This is extremely strong, but it has been proven in many cases that it exists. mean, it's a very active subject. And it's equivalent to the fact that the Hausdorff distance between the spectrum of this guy and the spectrum of this guy goes to 0. So it's stronger than the weak.
Before there was no, I mean, there was random when you said us. I mean, when you started out, you were giving us a theorem which had no probability in it.
Yeah.
Now you talk about strong convergence. So
Yeah, and
we're randomizing something.
yeah. So
Can you
I agree that strong convergence to now is
random notion? Yeah. So
it's not. I mean, it could be that we are able to prove at some point for deterministic things.
okay, I know.
Yeah, I know it's
your dream.
Yeah.
I know that's.
Yeah, I agree. But it's logic that because people in random graphs, I mean, you have.
I'm just trying to understand the statement. You said that it's known.
And
There must be a random statement.
no, it's not a random statement. The statement will assume strong convergence. So this is where we put our randomness, but the statement is deterministic.
So if you have strong convergence
Yes.
for your sequence.
Yes, exactly. So, and we also assume in the strong convergence, we also assume weak convergence. Although
The sequence of
weak and strong convergence. So, and the theorem is the following. So we assume first that rho n is strongly converging to lambda, strongly converging, okay? Then we assume one or two things more on the group. We assume that gamma has the rapid decay property. So it's a thing which is actually verified in many cases. I mean, it's a very weak assumption. It has the rapid decay property, and somehow it's something which allows you to control operator norms by L2 norms of P. Okay, something when you have this appearing, you can bound above by some L2 norm of P. So that's a convenient thing that is verified in most groups that are known. So free groups, polynomial growth, etc. Fine. Then we assume one more technical condition, but all these are what we prove. I mean, it's a long paper. We show counterexamples when we remove the assumptions. So so there is one more control of the resolvent, because at some point I said in the previous results on trees, you had to control the resolvent of the operator, and here also. So it's a technical thing, but we have to control I will not state it fully, but it's so RE plus I eta of the graph, the resolvent of the graph, between E and G to the fourth power times some power of the length of G. We have to control it when we sum over G in the group. We have to control, and okay, the resolvent is, again, we have some sum of, okay, it's here, it's A, it's in the infinite graph, and A is sum of PG lambda of G, okay? We need to prove, we need to assume that it goes to 0, equal to 0 in some limit, and it's in the limit where eta goes to 0, and it's a sup over E in the interval. Okay, there is some assumption on the resolvent, and under all these assumptions, this implies quantum ergodicity and quantum, and we need also to assume absolutely continuous spectrum, of course, in some interval. And under all these conditions, we have quantum ergodicity and quantum mixing for all observers. And in the interval, in the spectral interval I0, it's the same statement. Okay. So there are many assumptions, but for example, this assumption, which seems very weird, is something about the decay of the resolvent. And there is one example where it's not satisfied, it's ZD. And it's actually the only thing which is not satisfied in ZD, because if you take the approximation of ZD by boxes, growing boxes, this is verified, this is verified in GD, this is verified, this is not verified, and actually quantum mixing fails. And we have kind of, for all these assumptions, we have counterexamples. Of course, if you fail the absolutely continuous spectrum assumption, you also fail.
Tell me what if I have the spectrum's absolutely continuous and then there's some weird other spectrum elsewhere.
Yeah.
When you say strong convergence, you're restricting, so that's norm convergence for the functional calculus restricted to that? What's the definition?
No, it's a good question. We don't, we really assume strong convergence of the sequence of representations, but you see, it doesn't even see the sum,
So
the P.
Rejecting somehow?
No, we are not rejecting it, but it's a good question because strong convergence also doesn't see the P, meaning here I'm considering sum of G lambda of G, and you.
And on the free group, you could have an atom. And...
Yeah. No, it's a good question, but we don't assume. No. It's just strong convergence. And, okay, so I know I have little time, but I will try to say until the end of my time, maybe 5 minutes. I'm just checking. A very important thing is, okay, 2 comments. The first one is that we check also on concrete examples because, for example, this condition I said is failed on ZD. And so we had to find concrete examples where we are able to prove all this. So our concrete examples are free products, okay? Cayley graphs corresponding to free products. It's a generalization of the tree, but it has many cycles. Then there is one class of groups that is...
the free products is what McLaughlin did first, before anybody else.
Yeah, but actually we discussed this paper already, Charles.
Then was rediscovered by Voiculescu and many others, but he didn't trust.
We also, so we have a class of groups that are right-angled Coxeter groups, that is a strange class of groups where we can do all computations and prove that all our assumptions are verified. And
really, you know what the spectrum would say of a surface group is?
No, so it's not a surface group. So surface groups we don't do, but it's a specific class of right-angled Coxeter.
Special.
It's for which, in particular, we are able to understand the resolvent, although we have many cycles, etc. But the thing is, there is a symmetry argument that allows to prove that there is enough decay to show this. So we show somehow that there are many points G that are conjugated by automorphisms, and so this for many G's it has the same value. And since by the Ward formula, which is some formula relating the resolvent a bit like this, we're able to prove that this holds. So it's just to say that free products, of course, you could say it's quite close to the free group, but we're also able to prove it in other groups. And finally, we have an extension of these results to non-regular graphs, because from the beginning, I was considering Schreier graphs, and these are regular graphs. And also conversely, actually, all D regular graphs, or D, which is even, are Schreier graphs. But we also have an extension with a matricial framework where instead of PG, rho n of G, you consider a tensor product and PG becomes a matrix. Okay, it's this kind of adjacency operators that are converging to the same thing with tensor product. And then it allows you to encompass also Cartesian products and also lifts of a fixed space graph. Okay, so the bad point, and I guess Charles will not be happy, is that I didn't mention anything about the proof. I have 1 minute. No, I won't do it. I won't do it. I want to.
I have 5 minutes.
Okay, but I will. I had 2 pages of notes about the proof, but I can tell you the very beginning because it's a trick that everybody can take home. It's the following thing. It's a nice identity. So it's very basic. It's the following thing. If you have what we are considering in many places is the sum over alpha and sum over beta of phi beta, an, phi alpha. This quantity appeared a lot. We assume an, its mean is 0, and we want to understand this quantity. And maybe, okay, and I add a function of lambda because the identity will be true even for functions of lambda alpha, lambda beta, okay, f1, f2, two functions. These are quantities we consider. For example, f1 and f2 are the characteristic functions of the intervals we are considering for quantum mixing. This is actually just the trace of an, f1 of the adjacency matrix, an, f2 of the adjacency matrix. It's just a computation, and it tells you that this is a way to control the correlations. It's the two-line computation. You expand this guy, and this is functional calculus applied to the matrix A. Okay, A is just the phi alpha, phi beta are the eigenvalues, eigenvectors of A. And this is a computation that is true for any functions, for any A, etc. This is the quantity we want to compute, to bound above. We express it as a trace. And then the trace, of course, it's a double counting. You express it in terms of the diagonal of the kernel of this thing. Of course, the diagonal of the kernel of this thing is something complicated, but it turns out that we are able to express it as an, something, an, and here we have rho n, so we can put an also, sorry. Rho n of, instead of p, for example, if A was the sum of PG rho n, an was rho n of G, then we have some Q, actually, that is something different, but this quantity, we are able to express it like this. And this, to go from here to there, this is where we use the Benjamini Schramm convergence, actually. There is, I cannot explain to you now, but. And then when we have this quantity, this is where we can use either the asymptotic uncorrelation condition, because this makes appear quantities of the form an of x, an of gx, or we can use the strong convergence to bound it above by, for example, the norm of lambda of q. And then you want again to prove that this goes to 0, and then you use the rapid decay property to have it controls in terms of q in two norm. This is rapid decay. And actually this q, I didn't say what it is, but this q is related to the f1 and the f2 you choose. And the f1 and the f2 you choose are typically characteristic functions of the spectral intervals you consider in the definition. And actually, instead of the characteristic functions, which are things which are very singular, you would take the resolvent. The resolvent is a, so you would take for f1 and f2, you would take eta actually imaginary part of 1 over lambda minus you would take more, even better, eta square over x minus e square plus eta square. That's what you would take. And this is eta times the resolvent. This is f1 and f2. And if you compute, then you have an explicit q that is related to the resolvent. And this is why we need to assume this, because in the end, if we want to be able to prove that this goes to 0 when n, there is an hidden n that is here, you need to assume this. Okay, that's a 2 minutes sketch of the proof. And so just to conclude, I would say one word about not the perspective, but we assume absolutely continuous spectrum from the beginning. And we prove some things about the eigenvectors, but actually proving that there is absolutely continuous spectrum, this was your thing, is a very well-known problem in mathematical physics. Just, I give you a system, what is the nature of the spectrum? And this is not related to eigenvectors, it's just eigenvalues things. And this is the real stuff where physics happens, actually. And for example, on Cayley graphs, nearly nothing is known. about. This was the question of Peter before. There are very few examples where we are able to say the nature of the spectrum. So this is maybe the broad question that is open. Yeah. Cool, thank you.
Questions? There's a remarkable theorem of Aubert and what's the guy? Anyway, it's what they call it the measurable Keston theorem, where you prove the following converse. I wonder if you can see it in your machinery.
Again?
That if you have a sequence of Ramanujan graphs, they must converge Benjamini Schramm through the tree, the converse. Can you see that from your point of view? So you're assuming all about Benjamini Schramm, but there they're saying the converse. That if you have a sequence of Ramanujan graphs, it has to converge Benjamini Schramm to the tree.
But somehow,
it's something. But you know strong convergence.
Yeah.
If the C star algebra.
Yeah, so they're not assuming more than just the one operator, but if you assume more, yeah.
So yeah, if you assume more in this case, if you just have it could be that strong convergence may not imply weak convergence.
But it implies.
It is true if the algebra has a unique trace property. If there is a unique trace.
Yeah. Yeah, because just to complement many people don't put this in the definition. You prove that this implies this, so in particular Benjamini Schramm, when there is a unique, when it has a unique trace property. So it's
just proof. Take one operator.
Right.
Of the group and even of the group with a free generator, let's say.
I mean, this is quite remote.
It's a double now.
I remember telling it to Sarah, because he has a lemma in one of his papers, and I said, but then he said, but it's in my paper. I said, now you assumed the girth went to infinity. Then of course you've been Benjamini converge before you even start. Then he said, that's not obvious. Yeah, it's fine.
No more questions, it seems.